What up, what up? If you're in AP Pre-Calculus, and I assume you are, your teacher probably uses that guy over there, AP Classroom, probably to give you homework, maybe to give you quizzes. And at some point after the first 6 sections of Unit 1, your teacher will probably assign you what's called the AP Pre-Calculus Unit 1 Progress Check A. It's basically a test going over the first 6 sections of this unit. Okay, what this video is going to do is I created a bunch of examples that look extremely similar, not the same, so don't worry if you're a teacher and if you're wondering if I'm giving the same exact quiz or test or whatever. Nope. These are problems designed to look like the Unit 1 Progress Check A. So if you are a teacher, there's going to be a worksheet that I'm going to attach in the description. Download it, give it to your students, and then watch this video when you're done. If you're a student in AP Pre-Calculus and you want to test yourself before taking this actual test, you can download that worksheet, print it out, practice, and then watch this video and make sure that you're good. Okay, now I created these problems and I'm just going to go over how to do them. I'm not going to spend a ton of time reteaching anything. If you need to see anything retaught to you, go back to my YouTube and look for AP Pre-Calculus. Basically, I have one on 1.1 to 1.3 and 1.4 to 1.6, and it's called like Reteaching and Practice or something like that. And that should help you understand things a little bit better. For the sake of this video, though, I'm just going to do problems, look at every single problem, go over the answer, move on to the next one, move on to the next one, move on to the next one. So let's begin, shall we? Right off the bat, I have a picture, linear, linear, concave, linear. On what intervals is the rate of change increasing? Now, be careful with the verbiage. This is something I know I have to be careful of. Rate of change increasing does not mean positive slope. Rate of change increasing means concave up. So concave up appears to be in between that number, which is -1, and that number, which is +1. So the answer to this guy is going to be the interval -1 to +1 and only that. On which interval is the function decreasing at a constant rate? Well, it's actually intervals, and I know I said that, but I didn't say it. Decreasing at a constant rate means it's a linear straight line going down and to the right. That happens between here at -2 to -1. So let's write that out, -2 to -1. And it also happens here from 1 to 3. Union 1 to 3. Easy peasy. Find the average rate of change on the interval -2, which is u, to -1, which is u. The average rate of change is the straight line distance from the point represented by A on the left and the point represented by B on the right. The straight line distance has me going down 1, 2, 3 over 1. Negative down 3 over 1 is a slope of -3. Rate of change means slope. So the average rate of change, which represents a straight line, is going to be that straight line slope. Find an interval where the average rate of change is 0. There's two friendly answers, okay? An average rate of change being 0 implies a 0 slope, which is a straight horizontal line. So one obvious one, and probably the most obvious one, is between -1 to +1. So -1 to +1. But I could also say this guy, which is 0 to 3, because technically that's a straight horizontal line. I don't want to choose any other points because the numbers are a little iffy. I don't like iffy. There you go. Now I have one more color. I'll use all the colors. Find all the local extrema. The local extrema is any place where you have endpoints or maximums or minimums, or maxima or minima. So here's an endpoint. Here's a maximum. That's not. Here's a minimum. Here's a maximum. And here's an endpoint. So I have 5 of them. Okay, so let's list out all the local minima, local min. Okay, and we'll give the actual points. You're a local min, so negative 4, 1. You're a local min, so 0, negative 1. And you're a local min, so you're 3, 1. Negative 1, sorry. 3, negative 1. My local maxes, or maxima, is going to occur here at negative 2, 3. And also 1, 0. So pretty. It's such a pretty picture. Such a pretty picture. All right, list the zeros and multiplicity. Okay, listing the zeros means pretend that this is set equal to 0. We have ourselves a polynomial, a negative, factor, factor, factor. So my zeros are going to be whenever each factor is set equal to 0. So when I set u equal to 0, since that's just an x, it's just going to be the opposite, so negative 3. And this is going to be y minus 3 equals 0. Add 3 to both sides, x equals 3. Now, I'm going to write out x equals negative 3 with a multiplicity of 2. Now, what does multiplicity of 2 mean? Since the factor that gives you the 0 of negative 3 is being squared, that means it has a multiplicity of 2. Okay, when x is equal to regular 3, the multiplicity is 1. I don't know if I really needed to say that, but I'm saying it because make me not say it. Okay? A fast way of finding the leading term is you take whatever factor you're given. So my one factor is a negative. I have 2 x's and I have an x. So you take the leading term in every factor and multiply them all together. So negative from there times x again. So I'm multiplying both of these x's. So if this was 2x, I do 2x times 2x, but that's just regular x times x, and then times that x over there is going to be negative x to the third, which is my leading term. Now what this does leads us into C. This gives me a cubic flipped upside down, which is going to look something like that. Describe the end behavior using limit notation. So as x approaches negative infinity, that is basically me saying, where does my graph go as I move to the left without bound? Well, it's going up, which means as x approaches negative infinity, it goes towards positive infinity. As the limit of x approaches infinity happens, I am moving to the right without bound, which means I'm going down forever and ever and ever, and that's going to be negative infinity. Okay, and this is limit notation. Make sure you know limit notation. How many local extrema can be expected? Well, if this is a cubic, then I can expect a local min right there and a local max right there, and nothing more that's local. So 2. Okay. Now I'm going to sketch this graph. Now, when you sketch a graph, you are not making something that is 100% precise. You are just making an accurate representation of how the graph behaves. This is what I know from the previous slide. What I know is it looks like that. I also know that I have zeros at negative 3 and positive 3, and that the multiplicity at negative 3 is 2. So again, I know that my 0 of negative 3 right there and my 0 of positive 3 right there. I know since the leading term was negative x cubed that it's going to look like this. I also know that since the multiplicity is negative 3, when I start up here and I come down and approach negative 3, it's going to bounce right off and then come back. Since the multiplicity of regular 3 is 1, it's actually going to go through negative 3. So whenever you see sketch a graph, I'm not hyper-focusing on, well, what exact number is that? And what, I could find like the y-intercept if I wanted to. I could find the max if I wanted to, but sketch the graph doesn't really mean I have to. I'm not going to do it. Now, F kind of piggybacks off of what I did for E. Okay, whenever you are being asked to find where your function is positive or negative, you can draw yourself a little sign chart. Okay, this is called a sign chart, basically a number line. You mark out where your zeros were, -3 and 3. You remind yourself of what the graph looked like. So it looked like this, hit -3, actually hit -3, bounced back up, and went through +3. Perfect. Now, I care about where f of x is positive. F of x is positive everywhere above the x-axis, because that's where f of x is positive. Now, it's positive everything to the left of 3 except when I came down and hit -3, it became a 0 right there. 0 is not positive. So my guy is going to be -infinity to -3, not including it, and also -3 to regular 3, not including either of those. So it's positive at -3 to 3, -infinity to -3, not including it, union, and then -3 to regular 3. Let's move my face. Let's move my face. Let's move my face. 2 more factors are multiplied to f of x such that one of the zeros is, complex. 2 plus 2i. What are those factors? What are those factors? Well, first off, if one of the complex is 2 plus 2i, then the other one is going to be its conjugate, which means you flip the sign of the number in front of the imaginary term. So I have 2 guys right there. A factor is in the form x minus z, where your z implies 0. So if I wanted to use that and replace z with that one, then one of my factors is going to be x minus, little parentheses, 2 plus 2i. That's one of my factors, which would mean that another of my factor is going to be x minus z, where my light just turned off in my room, minus parentheses 2 minus 2i, close it, close it. Distributive property gives me a factor of x minus 2 minus 2i, and another factor of x minus 2 plus 2i. And so those are 2 more factors based off of the fact that I have complex numbers. This is my new dance. It's called Why Did the Lights Go Out and Why Won't It Turn Back On? I'll be right back. And I'm back. And we're given this weird-looking polynomial thing. Now, one of the things that I didn't say here, and I may not have said on the worksheet, is we are assuming that this is a polynomial. Okay, so now, which means smooth, nice, nothing crazy. Now I'm asking you if it's linear, quadratic, or cubic, so let's test it out. We test out the linearity by seeing what happens to get from one number to the next one every single time to see if the rate of change is the same throughout. So if I add 27, I get to that. If I add 7, I get to that. This is minus 7, minus 15, minus 17, minus 13, right? Yeah, that looks good. Minus 3, plus, I'm so bad at these, plus 13. Just making sure. Plus 35, plus 63. So not linear, not even close. Let's check to see if it's quadratic. Minus 20, minus 14, minus 8, minus 2, plus 4, plus 10, plus 16, plus 22, sorry face, plus 30. So not quadratic. So the rate of change over consecutive equal length input value intervals are not the same. So let's see if it's cubic. Plus 6, 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 plus 12. Just kidding, plus 6. So it is cubic. Oh, thank God. So now that we know it's cubic, it's a polynomial that's cubic, that's going to make answering these a little bit friendlier. What is the average rate of change on -5, 4? I will see another rate of change problem in a calculator section, so I'm going to make sure I actually write out the formula for this because I'm not sure if I'm going to write it out for the one coming up. This is the average rate of change formula over an interval. I'm going to label you A and I'm going to label you B, which means you are going to be A and you are going to be B. That would make you F of A and that would make you F of B. So F of B is 0 minus negative F of A is 27 over B, 4 minus negative 5. Double negative 27 is 27. 4 double negative 5 is 4 plus 5, which is 9. Rate of change is a positive 3. What is the concavity on the interval -4 to -2? Well, my average rate of change or my regular rate of change is always determined by looking at what I did on the linear side. If my rate of change is increasing, then the concavity is concave up. If my rate of change is decreasing, then my concavity is concave down. From these areas, I went from 0 to 7, which was 7, to -7 to -15. Those numbers are decreasing. 7 to -7 to -15 is a decrease of rate of change. My rate of change is decreasing, so concave down. And since this is a cubic function, we are going to have concavity twice. Use the zeros to write f of x as an equation in factored form. And since this is cubic, I can do this. Here's a 0, here's a 0, here's a 0. My zeros exist at -4, -2, and regular 4. So f of x is going to be x minus the opposite of each 0, just like we saw in the previous problem with the conjugate ones. So x minus -4 is x plus 4. X minus -2 is x plus 2. And x minus 4 is x minus 4. What is the leading term? Well, I have 3 factors, and we saw this in a previous problem. Always multiply the leading term of each factor. X times x times x is a positive x cubed. So it's a cubic that looks like this. Okay, let me get rid of the zeros. Let me just make let me make half of the Olympic sign. Oh, it's Mickey Mouse. Oh boy, says Mickey Mouse. Oh boy. What now? F of 6. Okay, so I don't have 6, but you know what I could do? I could either try to find patterns, or since I found out what f of x equals, I'll just find f of 6 this way. I'll just plug f of 6 into there. So I have 6 plus 4 times 6 plus 2 times 6 minus 4. That's going to give me 10 times 8 times 2, which is 180. Nope, regular 80 times 2, 160. And again, you could have done that by kind of figuring out the patterns here, but I found this to be easier. Describe the end behavior in limit notation. Looking at E, since I already said that my picture is x cubed, it's going to look like that. My limit as x approaches -infinity is going downward, so it's going to equal -infinity. And my limit as x approaches positive infinity, since it's going up and to the right, is going to be regular infinity. Okay? Fun. Fun, 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 as Rebecca Black reminded us. Is the function even, odd, or neither? Okay, an even function means. Is the function even, odd, or neither? Now, what an even function means is the picture that I have on the right side. If I were to take that and fold it over, do I get the same exact mirror image on the left side? Clearly, I don't. Now, the way that you would demonstrate what an even function looks like is f of negative x the same as f of x? Now, what this is saying, and this kind of goes along with that, if it's an even function, it's going to look like that. If x is right there, if I plug in negative x, is it going to be along the same y value? And an even function, it is. Here, it's not. Okay, so remember this little thing. I have a feeling that'll show up later at some point right there. All right, not even though, no problem. Now, odd basically means is if you were to take this guy and flip it upside down 180, do you get the same exact image? That's what odd looks like. I think it is, but I'm going to test out the odd formula just a little bit, which tells you that if I have f of negative x, will I get negative f of x? Now, what that would mean is, let's just say that I show my x right there as 1. F of 1 gives me negative 2. F of 1 gives me negative 2. What this is saying is, if I find out f of negative 1, will I get negative 2? Well, let's test it out. F of negative 1 is going to give me 2. Oh, looks very promising. So f of 0 is 0. So basically, it looks like this guy, if I were to pick any point, so if I were to look at here, okay, so at 1.5, I get 2. The opposite of that would be negative 1.5, negative 2, and it looks good. So again, the best way to view this visually is if I were to spin this upside down, would I get the same exact picture? And in this case, yes, I do, but we tested it out right there. I don't have the equation itself, so I can't see if every degree is odd. I can't see if every degree is even. It doesn't exist that way. What local extrema lives on 0.5? Oh, the interval, not the point. The interval 0.5 to 1.5. So my local extrema is going to be a min right there. So we will say a local min lives there, and that point is going to be the point 1, negative 2. Estimate the inflection points. Inflection points exist where you have a change in concavity. So this right here is concave down, concave down, concave down, concave down, concave down, and changes its mind right around here. Concave up, changes its mind right around there. Concave down, changes its mind right around there, and stays concave up forever. So me estimating my inflection points, I'm going to say that this will be negative 0.5. So I'm going to call you right there negative 0.75, negative 0.751. Looks pretty good to me. That is a point and not an interval, so I'm not going to do the union sign. Another point is going to be 0, 0, kind of obvious. And this guy would be the opposite, which appears to be 1.5, 1.75 down to negative 2. So regular 0.75, not 1, 0.75 down to negative 2. That's what my inflection points seem to look at. Estimate where the function's rate of change is decreasing. Now, rate of change is decreasing implies concave down. Not where it's decreasing. Rate of change is decreasing implies concave down. So it starts concave down all the way at negative infinity and stops its concavity at that point right there, which we called negative 0.75, close it, union. The other place where it looks like the rate of change is decreasing is going to be right there, and that starts at 0 all the way over to regular 0.75. Okay? The rate of change is decreasing means concave down. Make sure we know our vocabulary. Moving my face. The leading coefficient is going to be either -1 or 1. Okay, what is the leading term? All right, well, we need to find out what type of polynomial we're dealing with. We definitely have an odd polynomial because it starts down here and it ends up there. We also know we have a positive polynomial because it starts from the bottom, Drake, and ends at the top. So you're not an option. We go up, we hit 1 bump, 2 bumps, 3 bumps, 4. So when we have those distinct bumps, which we do, 4 of them, we can assume that the degree is going to be 1 more. So we are going to have a leading term of positive 1x to the 5th, or we will just say x to the 5th. Okay? Okay. All right, the function is decreasing on interval -infinity to -3.01 and increasing on -1.301 to 0.17. So, okay, it goes from the function is decreasing, so negative slope, not concave down, and increasing at this moment right here. What local extrema can be found at that moment? Well, if it goes from decreasing to increase, then that is a local minimum. Okay. What value does f of x approach as x increases without bound? Now, that is a gross-looking sentence, but what that means is as x gets larger, in other words, as the limit approaches infinity, what is my graph doing? I have a positive quartic. My highest degree is 4, and my leading term is positive x to the 4th, which means my picture is going to look like some kind of W-looking thing. So my limit as x approaches positive infinity is going to infinity. So my value is going to be, or my function approaches infinity as x increases without bound. And again, the phrase x increases without bound just means as x gets bigger, as x approaches infinity. This function has only 2 real zeros. How many complex zeros does this function have? Well, this is a quartic. So when you have a quartic, you are looking at 4 total zeros. And our options whenever you have 4 total zeros is you can have 4 real zeros and no complex zeros. That is one option. You can have 2 real zeros and 2 complex, or you can have no real zeros and 4 complex. In this case, we were told that we already have 2 real zeros, which means the only option that we could choose is 2 real zeros and 2 complex zeros. That's the only option that makes sense. So, if I were to draw this picture out, right, it might look something like this, where it crosses the axis at 1 0 and another 0, and then these guys would represent the complex numbers. Now, it gives us a complex number. If one complex 0 is -3 plus 5i, what is another? Well, it's conjugate. And you find the conjugate by flipping the sign in front of the imaginary number, so -3 minus 5i. That's the conjugate. Now, what we're going to do is we're going to take this function and we're going to plug away in our calculator. Okay, so part number 1, I'm going to take this guy and I'm going to use my calculator to find the real zeros. I'm going to not split the screen, I'm just going to cut away and come right back. And now it is calculator time. We're going to take f of x and hit the y equals to graph f of x, which is x to the 4th. So let's type that in. Don't forget to move out of the way. Minus 3x squared plus x plus 2. Okay? We need to find the real zeros, so let's graph that. The real zeros. Now, what I'm going to do is I'm going to zoom in. Let's see if zooming in just does the job. I'm going to hit zoom to and hit enter, and that does do the job for me. So I'm not going to overthink it. I have 2 real zeros, and this makes it look like I'm going to have 2 more complex zeros. I need to find U and I need to find U. So the way you find your zeros is you hit second calc and go down to 0 or just hit 2. And we're going to start with the 0 on the left. So the way you do that is you make sure your blinky cursor is to the left side of that 0. There. I'm going to hit enter. Move to the right. Hit enter. And for guess, it kind of gives us that little interval where our 0 lives in between those 2 bounds. And we end up with -7, 0, 2, 1. And since this is pre-calculus, we'll do -7, 0, 2. -1.702. Got to get that whole thing in there. So that's one of my zeros. Let's find the other one. Second, calc, hit zoom, go to the right, hit enter, go to the right some more, hit enter. Our 0 is in between that interval that was just created, so hit enter for guess, and I have -0.7183, so -0.7183 is going to be our guy. All right, so my graph crossed the x-axis in 2 spots, -1.702 and -0.7183. That's where it crossed the x-axis. On which intervals is the rate of change positive? A rate of change being positive just means it's increasing. It does not mean the rate of change is concave up. Rate of change is positive. So for this one, we're finding the intervals, there goes my light again, where the rate of change, the slope is a positive slope. On which interval is the rate of change positive? So let's make sure that everything is in for y equals. Hit graph. I turn my zoom back to normal. The rate of change being positive implies that it is just increasing. Now, I know most of us would look at this and think rate of change being positive, is that concave up? Nope. Rate of change positive means increasing. So let me zoom in again. I probably should have zoomed out in the first place, but I'm going to hit, not second, but regular zoom and zoom in. So I'll hit 2, I'll hit enter, and that should be good enough for me. Now, your rate of change is positive or your function is increasing at a minimum. So it's very important that I find out what the minimum is. So I'm going to hit second calc and find out one of my minimums. So my minimum, if I hit 3, I can find by hitting the left button a bunch of times. And I'm going to find this minimum right here first. Hit left a bunch of times. Okay, so you're now to the left of the minimum. Hit right a bunch of times until you're to the right of the minimum. And so now this is saying my minimum is going to live in between these. So hit enter on that. And my minimum is -1.3008. So the left side of my interval is going to be negative, and I'll round it to -1.301. Okay, so it's going to be positive from here to that guy. Now, what's that guy? That's going to be a maximum. So let's second calc and do the same thing, but for maximum, which is 4. So I'm going to go right a little bit. I'm going to hit enter. I'm going to hold down right until I pass the maximum. Hit enter on that. And now my maximum lives in between those 2 intervals. Hit enter on that. And my maximum, according to Mr. Calculator, is 0.1699. So I'm going to call it 0.170. So that is one of my intervals, okay? Between it was -1.301 to 0.170, positive. All right. Now my next increasing interval is going to be, this is decreasing, so I need to find this minimum and say that's going on until infinity. So let's find the minimum right here. Second, trace, let's go to minimum, so 3, go to the right a little bit, hit enter, go to the right a bunch, hit enter, enter again, and it gives me a minimum of 1.1309, so I'm going to say 1.131. And that is going to go all the way until infinity because this is a quartic equation. So in a second, you'll see me write down what my two intervals were, and I had to use the calculator in order to do it. Okay, so we used a bunch of max and min stuff to find out that we have positive slopes at negative 1.301 to 1 or 0.170. So that's one interval union. And then we have 1.131 going on to infinity as x increases without bound, as we saw in the previous slide. Find the average rate of change on negative 3.52. Now, the average rate of change is going to be found by using the formula f of b minus f of a over b minus a. So what I'm going to do is I'm going to use a table to find f of b, which is going to be f of 2. That's going to give me a number, minus f of a, which is negative 3.5. And then I'm going to plug in all of those values and find out what I get. All right, now my job is to find the average rate of change. What you could do is you could take the function and plug it all in, and I think everybody here would know how to do that. But what I'm going to do is I'm going to use my table to find the rate of change. My rate of change happens Okay, for problem G, for number G, I'm going to have to find the average rate of change on the interval negative 3.5 and 2. Now, what you could do, and everybody would be able to do this if you are in this class, if you use this calculator before, is just, plug stuff in, but I'm not going to do it that way. I'm going to allow my table to do the talking for me. Now, here's the issue. If I were to hit second table, it does give me a value of 2, but it doesn't give me a value of negative 3.5. So this is what I'm going to do. I'm going to go up here to table set. So hit second window, and it allows me to change my table setup. This little triangle means delta. It means the change of the table. I'm going to change that to 0.5, which means it's going to start at negative 4 and change every 1/2 x value. So when I go back to table, I now have my negative 3.5. So let me go down, let me go over, and I'll get more exact values. Negative 3.5 is going to be 111.813. And I'm going to go down to 2 and get 8. That's nice. Now I'm going to use the average rate of change formula. Okay, which is f of 2 minus f of negative 3.5. So I'm going to go over here and type that all in. F of 2 was 8 minus negative 111.813. Close that. We're going to divide that by 2 minus 3.5, 2 minus negative 3.5, and that gets us a rate of change of 21.7841. So 21.784. Math ended up being 21.784. Fun, fun, fun. Find all local maxima. We kind of did that. We're going to do it again. Find the local maxima. Well, we kind of already did it. Let's do it again. And there's only one maximum that's local. If you're like, well, what about this one? What about this one? Well, that is infinity and that's infinity, so it's not local. So I need to find just this maximum right here. So we'll quick do it again. Second calc takes you to calculate. I want the maximum, so I'm going to hit 4. My maximum lives right here, so I'm going to make sure my cursor is to the left of it for the left bound. Hit enter. I'm going to make sure my cursor to the right of it goes beyond the 0, and not the 0, the maximum. And guess, always hit enter. And it gives me a maximum of 0.169, so I'll call that 0.170. And let's do the whole point. Let's do the y value too. 2.084. No worry, no need to round there. It is 2.084. So the point, that is going to be my maximum. Let's write it out. There was 1, and the local maxima was at the point 0.170. The point 0.170, 2.084. Okay, let's move my face. Let's move my face. Let's move my face. Interval A is denoted as negative infinity to 0. Interval B is denoted as 0 to infinity. So we'll see what that looks like on our graph and find out the interval where the rate of change goes from decreasing to increasing. All right, interval A is denoted as negative infinity to 0, and B is denoted as 0 to infinity. So let's hit graph and have a visual. So interval A is to the left side of the y-axis. Interval B is to the right side of the y-axis. On which interval does the rate of change go from decreasing to increasing? Now be very, 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 very careful. The rate of change going from decreasing to increasing does not mean I'm doing this. I am decreasing and now I'm increasing. No, that's if the rate of change is negative and goes to positive. The rate of change decreasing implies concave down. So right around here, I start being concave down and it stops right around here. Now, right around here, I begin being concave up, which means starting from right around here, my rate of change is decreasing, and starting right around here, my rate of change is increasing. So to answer this question is on this point right here is where my rate of change goes from decreasing to increasing, which implies interval B. Okay, so a rate of change going from decreasing to increasing represents, this is a decreasing rate of change, and this represents an increasing rate of change. So as I said, we care about where the inflection point is. And the inflection point happened to the right side of the y-intercept or the y-axis, so interval B seems to be my guy. All right? All right. So the last one. The Ferris wheel problem. Let me move my face. Let me move my face. We have a picture of a Ferris wheel. Okay. We are going to assume with this Ferris wheel that at the very beginning, we are sitting at a bucket at the very, 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 very bottom of the Ferris wheel. Now, what we need to do is we need to find the height of the bucket at the beginning of the ride and find the bucket at its maximum height. It gives me a diameter of this Ferris wheel of 50, which means its radius is 25. So if my center of the Ferris wheel is at 30 feet above the ground, that means the bucket is 5 feet off of the ground. So the beginning of the ride is going to be 5 feet above the ground. So you're 5 feet, okay? You're 25, you're 25, which means the maximum height is going to be 5 plus 25 plus 25, 55 feet. Okay, so that's where we are. At the very bottom, we're at 5, and at the very top, we're at 55. Sketch a graph that shows the first 3 revolutions of the Ferris wheel. Use time t for the x-axis and height h for the y-axis. You do not need to label specific values for t, thank God, but label specific values for h. So I'm going to write out, this is going to have to be a big one, your t. I don't care about time. I'm going to label specific values of 5 where it's at the very bottom, 30 where it's in the middle, and 55 where it's at the very top. Okay. Now, what's going to happen as this guy rotates is we're going to start at the very bottom, go to the middle, go to the top, come back down to the middle. So imagine it's basically like this. Okay. You're starting at the bottom. So as you go up, and it doesn't really matter which direction you go at all. So if you're like, does it go clockwise or counterclockwise? It really doesn't matter because you're going to start at the bottom. You're going to reach the middle. You're going to hit the top. You're going to come back down, and then you're going to hit the bottom again. So basically, you have this wavy thing that starts at 5, goes to the very top. Oh, boy, not happy at all with the way that turned out. Let's try it one more time. Even though I don't know why, it's not going to look good either way. Let me make it a thick line. That helps me see things better. Then come back down. Repeat. Repeat. There you go. Okay. So it's not going to win any awards for looking good, but it's accurate enough where I, a math teacher, I'm like, that works for me. Okay, so what do the inflection points imply in the context of this example? The inflection points are where it changes concavity. So it was concave down here. I'm sorry, concave up here. Then all of a sudden switches to concave down. Then all of a sudden switches to concave up. Then all of a sudden switches to concave down. Then all of a sudden switches to concave up. Then all of a sudden switches to concave down. Then all of a sudden switches to concave up. End. So what do the inflection points imply at the context of this example? Well, all of the inflection points happen to be at the same exact number, 30. So what do they imply? Well, they imply that you or the bucket are 30 feet above the ground. That's what it implies. Explain why there are no zeros. Well, 0 means the ground. If you had a Ferris wheel that hit zeros, that means you would hit the ground. Why are there no zeros? Because you ain't hitting the ground. Listen. I'm going to get all straight up gangster on you and put hitting ground, cuz the bottom, the lowest point that we go is 5 feet, not the ground. We never at one point skip off the ground. So a 0 would imply you're hitting the ground. From here on out, I'm going to let the calculator graph this guy to find the absolute maximum and then the absolute or the local minimum. All right, let's handle this very last problem, which has to do with the Ferris wheel. We're given this equation, h of t. I'm going to want to graph it because it's asking me to find max and min. So I'm going to hit y equals. And obviously, instead of h and t, I'm going to use x and y. So I'm paranoid about, fractions. So negative 1 divided by 18, close it, x squared instead of t squared. Plus, and I'm going to do parentheses again because, paranoid, 10 divided by 3, close it, x plus 5. So let's hit graph. I hate it. Now, there's something that I definitely know about this problem. I know that if this is dealing with the Ferris wheel, right, it looks like it does start at 5, which kind of makes sense. Our height is 5 at, time 0. But I also know it goes all the way up to like 55. So let's zoom out until we see it touch down. So it's going to go up and it's going to come back down. So let's zoom out, hit 3, hit enter, and still no good. So it goes up. At some point, it's got to come back down, and touchdown hasn't happened yet. So let's zoom out one more time, zoom 3, enter, and there we go. Now, obviously, I kind of want to do a little bit better than this picture, and we haven't done it yet in this video. So let me make my window fit my problem a little bit better. I'm going to go to trace and have a general idea as to where it touches down. All right, so it comes back down and hits the x-axis somewhere in the mid-60s, my age. So I'm going to go to window and I'm going to fix everything. My x-min, I'm going to make it -5 so I can go back to the past a little bit. And since it was mid-60s where it touches down, I'm going to hit 70. Now, keep in mind, I know in real life this problem's never going to touch the ground. I just want a good visual in front of me. My y-min, since ground level is 0, and technically I'll never hit the ground, I'll use 0. And since I peak out at 55 feet, I'm going to use 60. All right, so a little to the left of where I start, a little to the right of where I start. I'm using the ground, and I'm using a little bit more than my maximum height. I'm going to hit graph now, and much better. So the first part of E is asking me to find the absolute maximum. Since this is a quadratic with a negative leading coefficient, I will have a absolute maximum, and it lives right there. Let's find it. Second, calc allows me to type in my maximum, so 4. Left, 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 left. Make sure you go to the left of where your maximum appears to be. Enter. Go to the right a bunch of times, to the right of where your maximum appears to be. Hit enter, and I get 29.999999999. Now, I'm no genius, but I think 29.99999 is 30. Now, what that means is if it's 30 at 30 seconds, because T is in seconds, at 30 seconds, I am at 55 feet in the air. Okay, that is what the absolute maximum means. And that kind of makes sense, in the context of this problem. Now, I'm going to use the graphing calculator to determine and describe all local minima. Here's the thing that I have to be careful of. Okay, my interval that I care about is going to be between 0 and 60 because I only care about the first revolution. Okay, which means it starts at 5 and ends at 5. So my minimum happens at 5. So I'm going to go to the left, or I'm going to go to calc rather, and I'm going to hit the value button. Now, common sense tells us that at the very beginning, I'm at a minimum. So when T, or in this case X, equals 0 seconds, I'm at a minimum, and that minimum is 5 feet in the air. That makes sense. So at 0 seconds, I'm 5 feet in the air. Now, if I go up to 30 and come back down, that's going to be 60. So without using a calculator, I'm going to use it anyway. I'm going to hit calc, I'm going to hit value, and 60 is going to be my other local minimum. And that's also 5, which makes sense because we can't go any lower than 5 feet. Otherwise, we have a severe issue with our Ferris wheel. All right, calculator time over. All right, so the absolute maximum was the point 3055, which in a real-world context means 30 seconds into the first revolution, you are 55 feet above the ground. The local minima is where are you at the very bottom? Well, at the very beginning, you're at the very bottom, and that's 5 feet above the ground. And also at the end, 60 seconds later, you are 5 feet above the ground. Okay? So again, this is basically all of these problems cover what you should expect to see on this exam that you're probably going to be given if you're an AP Pre-Calculus. If you need more help, go to my videos, a link in the description of me reteaching things. So maybe that'll give you a little more clarity. Okay? I appreciate you guys. Thanks for watching. Stay blessed. Bye.